Okay, so today what we're going to do here is we're going to learn how to go ahead and break up ions. Okay? Break up your ions when you're when they are aqueous solutions. Aqueous solutions. So let me go here. Probably should start on the other page. So what we're going to do is we're going to see. We talked about aqueous substances last week, and we're going to kind of see how when an aqueous substance is aqueous, it's in water, it's broken up into its ions. And it's important to be able to write out the individual ions because they're going to be part of our next worksheet when we're making what's called net ionic equations. So we're going to start off here by what we're going to do right now is going to learn how these aqueous substances are all broken down to their ions. I forgot to put that it's aqueous here, and how they're put into their ions. So let's go ahead and show how that works. First off, let's kind of explain basically what happens. Whenever you have a compound, an ionic compound, let's call it compound AB. The A here is going to stand for the cation. All right, and remember the cations are positive. And cations generally tend to be metals. They tend to be either metals or the one exception we have is the polyatomic ion ammonium. Okay, so that's what ends up being the A substance. We always write the cation first in our formulas. The B is going to be the anion, and that's your negative ion. So it's a cation and an anion, and usually these are nonmetals, or individual nonmetals or polyatomic ions. Atomic ions. Okay. The exception to that, that the polyatomic ions are negative, is ammonium. And what you're going to do is when you see that a substance AB is aqueous, what that means is when you put it in water, it's going to break up into cation A with some positive charge. It could be plus one, plus two, or plus three. Right? We know that cations could be plus one, plus two, or plus three, and anions, which has a negative charge to it, negative one, negative two, or negative three. Okay, here I put a plus one and a minus one because remember these guys are neutral, and that's because we have just enough positive ions and negative ions to make them neutral. Okay, so this is what happens: you put this substance into water, and it breaks down into its ions. Okay, and so that's what we're going to do with all these other guys. In order to be able to do your net ionic equation worksheet for tomorrow, the main thing is to be able to break down ionic compounds into the ions, because later on we end up canceling ions and stuff. So that's kind of the important thing. So let's go ahead and uh, see how we would go ahead and go about doing the five that I had above. The first one in that list I had was sodium chloride. Now I start off with sodium chloride because it's pretty easy. Two elements, right? There's sodium and chloride, so I can just basically do, okay. There's two elements. Um, the first one is a cation. Second one is the anion. If I look up Na is sodium, and it's in column one, so it gets a plus one charge. So I write out as plus one. Remember, these are the same rules that we learned first semester. When you get the charge, sodium is always a plus one because it's in column one. Chlorine's in column 17, and so you would end up writing it as 17. So you can kind of write it as a chemical equation, although this is kind of like a step before your chemical uh, reaction takes place. This is kind of like the how things are set up in what we call aqueous solution. Aqueous solution. A solution is a mixture. We'll talk more about it later on this semester. But whenever you hear the word solution in chemistry, it's a mixture. Right? You can think of it this way. Here we have our beaker. So we have a little container, a little beaker here, and you have some sodium chloride solid. You put it in water. Let's go ahead and put some water in here first. Then you put the sodium chloride in there, and these break up into sodium ions and chloride ions. sodium ions and chloride ions. And they're all kind of swimming in every direction. So each one's going its own way, and they just swim around. Okay, so that's what this represents. The sodium chloride breaking that's only two elements. So one of them is going to be the cation, the other one's going to be the anion. This one's pretty easy. But that's the basic idea. And all these problems that you're going to be doing, whenever you have an aqueous substance, this is aqueous, it breaks up into two ions, one and two, and that's it. Okay, never more, never less. It's kind of like the Sith. Always two of there is. All right, so let's try another one. Let's see. We said another one was KBr, KBr, KBr aqueous. And this is what your worksheet's going to look like. I'm going to give you KBr aqueous. What does it turn into? And so what you have to do is break it up into the two ions. Once again, this just has two elements, K and Br. So you just have to figure out what K is, potassium, and what the charge on potassium is. Once again, it's in column 1, so it's +1. And Br is bromine. It's in column 17, so actually remember we call it bromide. And since it's column 17, it gets a -1 charge. That's all there is to it. Now they get a little crazier once you start using subscripts. So FeCl2 aqueous. What does FeCl2 turn into? Once again, only two elements, so we're basically breaking it up into two ions. If you look up Fe on the periodic table, and maybe I should have had a periodic table here to look at, but in the interest of time, I don't have one actually. Here, let me go ahead and get one here. All right, I think I can get one here real quick without spending too much time. So go ahead and do that. Up here in the uploads folder, I have a bunch of stuff that I put up for you last semester. All right. Now, I'm just waiting for it to open up here. There you go. So here's our periodic table. Here's Fe right here, iron, and Cl is chlorine. All right, so it's iron and chlorine are the two elements, right? Now, iron is a transition metal, right? It was right here in the middle. We don't know what the charge is going to be on here. Could be +2, could be +3. But chlorine, we know, is in column 17, just like we saw earlier. So we know that we're going to actually come up with a chlorine with a -1 charge. So chlorine gets a -1 charge. Now, there's two chlorines here. And so this 2 chlorine implies that there were 2 chlorides. Basically, these are empirical formulas, which means the empirical formulas are just telling us not that there's 2 chlorines stuck together, but there are 2 chlorines for every iron. So when they get liberated from each other, right, when they're in the solid crystal lattice, they get free from each other. Both the chlorides go their separate ways. So I put the 2 in front instead of putting it as a subscript. Instead of putting Cl2, Cl2 would connote. In other words, it would basically kind of imply that the chlorines are together. But since the chlorides are all separate, one over here, one over here, so there's one here, there's another here, this one could be going that direction, this one could be going this direction. They're free from each other. I put the 2 in front to show that there are 2 separate chlorides. And now that we know that we have 2 chlorides, and each chloride is a -1 charge, that must mean that there's 2 negatives here. So that iron should have 2 positives. Remember, during the chapter 8, we had to figure out how to name it. And so we had to figure out the charge. So this is iron 2 as opposed to iron 3. We're kind of having to do the same thing, except that right now, really, your worksheet's not asking you to name it, although now you know it's iron 2 because it's got a +2 charge. But it's mostly what you're doing here is you're showing the charge on it, and you're separating out the cation from the anion. So as I said, and I'll do it like I did earlier. So once again, sorry with my goofy little beaker. I'm not the greatest artist to begin with, and then now with this little tablet, it's even harder. But let's say I have this chunk of FeCl2 in it, and remember that when they're in a solid, they are all these ions are right next to each other. All right. And some of these are iron, some of these are chloride. There's twice as many chlorides as irons. Once you put them in water, it liberates them. So there's an iron that goes its own way, and one of the chlorides goes here, another chloride's here. If we want to draw more, we could. If there's a second iron, there's two chlorides that go with this. Always twice as many chlorides as irons. Okay, that's what the two is basically showing you. Once you put them in aqueous, then there's three ions here. All three of them separate from each other. Okay? And once again, that's why I put the two in front of here. And that's going to be important in doing our net ionic equations. All right, so that was another example. So FeCl2, which other should we do? Let's try some polyatomic ions. So when you have polyatomic ions, like CaCO3, when you have something that is aqueous, well, I just realized this one's, oh, never mind. The other two examples, or the other three examples, basically had just two elements. This one has three elements. There's calcium, there's carbon, and the oxygen. But as I said, you break them up into exactly two ions. So if we need to get two ions out of it, which are going to be the ions, right? We're not going to break it up into calcium and carbon and oxygen ion. There's got to be two of them. Usually what happens is the first element is a metal, and the metals are usually not part of the polyatomic ions, although there's exceptions, like with permanganate. But usually the first element is a metal, the rest is a polyatomic ion. And you'll recall that we had polyatomic ions that we learned about. And I told you it was going to be important to learn about them and later on, because they're ubiquitous. They're found all over the place. And so if you'll notice, this ion that we get from breaking this up, CO3, does that look familiar, CO3? Well, if we go to the polyatomic ion page, CO3 is right here. And CO3 is carbonate and has a -2 charge. Okay? And calcium, Ca is calcium, going to the periodic table here. Ca is calcium, and it's in column 2, so that tells you it's got a +2 charge. So calcium gets a +2 charge, and carbonate gets a -2 charge. And so the tough part about this is that people usually go, wait, how does that work if I've got three elements? How do we break it up into two ions? Well, one of the ions has more than one element in it. This is a polyatomic ion. So it's got carbon and oxygen together make up the whole ion. Okay. And this time the subscript is part of the ion. If you go back to this polyatomic ion chart here, the subscript 3 is part of the whole ion. So it's not like there's three, it's not like we have to put the 3 in front like we did for the chloride, which we had up here. Over here, we had two chlorides. The two told you that there was two chlorides in it, but each chloride ion was a single atom or monatomic ion, but on its own. The 2 in front tells you that each of these guys separate on their own. Now, for the carbonate that we have right here, there's just one carbonate. There's 3 oxygens in it, but there's just one carbonate. So we keep the 3 down here because it's part of the polyatomic ion. So whenever you see the polyatomic ion have subscripts in it, don't separate it from the rest of the formula. Okay. Now we got another one here that it kind of shows you when you should do that, when you shouldn't. All right. So K2CO3 is aqueous. K2CO3 is potassium carbonate. Okay. So we still have our carbonate ion in there. That's one of the ions. And the other, once again, we're breaking it up into 2 ions, the carbonate and the potassium. So the first element is a metal. Separate the metal from the rest of the substance. Okay. And so now we're going to have potassium and carbonate. We know that carbonate like we saw earlier, is CO3 with a -2 charge on it. Potassium is an element in column 1, so we give it a K plus 1. Now, this 2 is different from this 3 in the sense that this 2 is only here because we needed two plus 1 charges to make up for the -2 charges, the 2 negative charges on the carbonate. So this basically tells me there are 2 potassiums for every 1 carbonate. So when they're liberated from each other, I put the 2 in front here. Okay, so see how I put the 2 of the potassium in front to show there are 2 individual potassiums, because every potassium is a plus 1 charge. There is no K2 ion. It's a K ion. It's a potassium ion. When they are monoatomic, in other words, they're ions made up of one element at a time and one atom at a time, then we when we liberate them from each other, when we make it aqueous, then each of the ions go separate. This 3 doesn't get separated, doesn't get put in front because this is part of the whole polyatomic ion. So that's another one. Let's do 1, maybe 2 more. Sometimes you will see one that looks like this. Okay, this is strontium acetate. And you'll notice that this one has, I have to put a 2 there. Okay. This one has parentheses around it. And the reason that this one has parentheses around it is because we need 2 of, this is a polyatomic ion, and we need 2 of them. So once again, if you look at this one, you're breaking it up into 2 individual ions. There's a SR, which is strontium, and strontium is in column 2 on the periodic table. Once again, I can go ahead and go to the periodic table. Here's strontium right here. And it's in column 2, so it gets a plus 2 charge. I can write it as strontium plus 2. And then over here, this whole thing is C2H3O2. If we go to our table over here, sorry, polyatomic ions right here, C2H3O2 is the acetate ion. So once again, there are 4 elements in the that formula. 3 of them are all part of one polyatomic ion. So C2H3O2 is the polyatomic ion that we're going to work with. The whole thing together is a polyatomic ion and has a -1 charge. That's why there's 2 of these down here, because the strontium is a plus 2, so therefore we need 2 -1s to balance it out. But each one of them goes their separate ways. Actually, I think it's pretty easy when there's parentheses. Whenever you see parentheses, what it's telling you is that inside the parentheses is a polyatomic ion. And when you liberate them, when you break them up in aqueous solution, there's going to be 2 of them. So I put 2 of them, and each one goes its own way. Right? And the strontium is over here. So that's how you're going to be doing the problems today. You're going to go ahead and take the formula, break it up into 2 ions. Once again, always 2, never more, never less. Just like the Sith, those Star Wars fans. Break them up into the cation, which is usually just a metal. The only exception would be ammonium and H4. And whatever's left over here. Whatever's left over here is going to be either one element and an anion, like these guys over here. And you just have to find out what column it's in to figure out its charge. Or it'll be a polyatomic ion, like these guys. Okay, so I hope that helps.